Hello everyone, this is Jannick Schmidt speaking here. Now I would like to welcome all of you to our webinar on 10 years of modeling of indirect land use changes. I will be giving this webinar together with my colleague Michele de Rosa.
Welcome everybody.
Good. We have put together an agenda, which you hopefully see now. I should share my screen. I will start giving a short introduction and background. After that, we will define a couple of terms. So what is direct and what is indirect land use changes? After that, we'll go through the model we have been developing over the last couple of years with key assumptions, markets for land, looking into temporal issues of land use changes and emissions and how to model that. After that, we'll go more into details on how to use the model, really show like hands-on, how do you use it step by step, showing it simple to use the model and some application examples. And then in the end, we'll be talking about new developments and what is the next. So, the background of indirect land use changes and of this webinar is that we are facing a really high impact relating to land use changes. One example is that around 11% of global greenhouse gas emissions are related to land use changes. So we're having a really high impact. What are the causes of this impact? The causes is that we are facing a global increased demand for land, and when we see a change in demand for land, then we will also see land use changes. So that's the logics. The challenges. Currently, if we look in LGAs, not very often land use changes are included. So, and that is, of course, there's a good reason for that. And that's why, because we have some challenges. And the challenges are that it's often hard to ascribe the land use changes to their drivers, and also hard to say, for instance, what is the role of energy, food, fibers, whatever we use land for. Here's a picture of what the globe looks like. So you can see with the colored indications in the top, in the picture in the top, what is cropland, what is pasture. Below in the picture, you can see how or what is the total global land use, how is it distributed. We see that we are using 17% of our land area for crops, 35% for pasture. And we have a large area, which is savanna, barren, or built-up land. And then we have the 42% of forests. To the right, you see how current forests are composed, that we have a majority, which is naturally regenerated, mainly secondary forest. Then we have primary, where we see the high biodiversity. And then we have 3% planted forests. Moving on to the next slide here. With this slide, I will just briefly elaborate that land use changes is not only about greenhouse gas emissions. For instance, you can also see here that 9% of global forests have been lost since 1961. Current species extinction is up to 7%. It's global extinction, and forecasts, they indicate that we will lose up to 1/3 of all species already by 2015. So we are really facing some major impacts. And not only biodiversity and greenhouse gas emissions. Currently, a quarter to more than 500,000 people are dying because of landscape fires, and that is highly related to land use changes, where fire is used for clearing land. In the picture below, you see how the increase in arable land and at the same time a decrease in forest area. So there's a clear linkage between deforestation and loss of land. Is this a topic that will just disappear within the next couple of years? Probably not. All forecasts show that we'll see population growth. We will have economic growth, which will, for instance, lead to more food consumption per capita, and also increasing the share of meat, all which will require more land. On top of that, we also have biofuels, and of course also other fiber-based materials. So there's nothing that tells us that it will be an irrelevant problem in the near future. All these problems, they led to the establishment of what we call the Indirect Land Use Change Club in 2011. It was launched. It is our crowd-funded initiative where we are based on membership subscriptions that will create budget for developing the model. So currently we have around 25 members of our crowd-funded crops, and it's still coming new members, and we are still developing and refining the model. And there's more information in the web page below. Good. Now my colleague Michele de Rosa, he will go into, so what is the direct and indirect land use changes?
Thanks a lot, Jannick, for this very comprehensive introduction. So now let's take a look at what is actually the difference between direct and indirect land use change. Let's do this with an example. Rapeseed, for example, for 1 hectare of satisfying the demand of 1 hectare of additional rapeseed. What we do in that case is we cultivate 1 additional hectare of rapeseed. Therefore, we occupy a piece of land that is already in use somewhere in the world. And this is what we call the direct land use change effect. So what takes place on that spot. Now, of course, in doing so, we will also displace the production that was occurring in that piece of land before we occupied for rapeseed production. This displaced crop is still demanded by the market, that therefore will be produced somewhere else in the world. Now, where is this somewhere else in the world? Well, this will trigger a domino effect, which will partially end up with the occupation of further land at the frontiers, for example, in the Brazilian Amazon, to supply the displaced production. And this is what we call the indirect land use change. And partially will also lead to the intensification of some land that is already in use through intensification, through the addition of fertilizer, therefore the intensification of the production. This is also indirect effect. So the indirect effect is both the intensification of land already in use and the occupation of land at the frontier. Now, before explaining how do we model land use change, let's take a look at what are the current practices and why they are wrong. So first of all, the current practices are what past 2050 greenhouse gas emission protocol and PEF guidelines do. What they basically do is, if you want to know what is the land use change effect of 1 hectare occupation of 1 hectare of land in 1 year for crop production, what they do is, first of all, to choose an amortization period. Let's say 20 years, it's probably the most common. Then they determine whether the land use change is included or excluded. That means that, for example, if we occupy 1 hectare of land in 2017, we account for the history of this piece of land in the last 20 years, so from 2017 all the way back to 1997. And that means that if in 1997 there were no forests on this hectare of land that we are occupying today, then there is basically no land use change. So in this case, land use change will be excluded. However, if there was partially or completely forest in this hectare of land just the year before, there would have been emission just the year before we are considering that are systematically excluded. On the other hand, if this forest was deforested in 97, instead land use change would have been included. So that's what is currently the most common approach. If land use change is included, then at the moment the practice is to identify the change in carbon stock before and after the land use change occurred in determined period of years, as we said, for example, 20. And then, based on the delta carbon stock, calculated the greenhouse gas emissions, as shown in the formula. Now, what are the limits of this approach? Well, in short, the limits are, first of all, that the amortization period could be in the past or in the future from the year that we are demanding the biomass. So from here we are occupying the land. So for example, it could be 20 years in the past from now or 20 years in the future from now. This is an interpretation issue that remains open. Second, the amortization time period is the choice of the amortization time is arbitrary. So why, for example, 20 years? It could be 30 or 10, changing, of course, dramatically the results. This also means that the choice of the amortization period also affects the reference scenario, because as we have seen in the picture I just showed before, if we account for a reference amortization period of 20 years, and the land use change occurred 1 year before the 20 years, then we are basically assuming a reference scenario of no change, so the same reference scenario as a reference scenario, the same land type as is today. While if we assume in this case 30 years, we would include instead as a reference scenario the partially forested land that's shown in the picture. So the reference scenario is chosen arbitrarily just as the amortization period, as a consequence of the choice of the amortization period. This approach also ignores any relationship and substitutability of products and the trade between crops and animal products, because only accounts for what happened in that determined piece of land. So what are the consequences of all this? The consequences are that with this approach, we systematically overestimate the land use change at the frontier. So if you occupy a piece of land in the frontier, then you do account for it because you pass from forested to non-forested land. While instead we ignore the indirect land use change for established arable land. Now, Jannick can provide more insights on what is the difference between this approach and our indirect land use change model.
Thank you, Michele. So now we can say that the scene is all set. We are ready to go more into depth with the land use change model we have been developing over the past years. I will start to give a very brief overview of what are the key assumptions. Actually, there are very few key assumptions in our model. After that, I'll go more into detail how we are dealing with markets for land. That is something which is commonly not done. Secondly, I'll talk about reference flow and functional unit of the model. And after that, going more into detail with temporal issues of land use changes. Good. What I do in the slide here is that I will just explain the model in 5 bullets. So that's the 5 key assumptions we are dealing with. First of all, we say and assume that land use changes are caused by the demand for land. I've spent quite some time in Indonesia, Malaysia, and I've seen land use changes, and I can assure you, this is not fun. It's not fun clearing a forest. It's hot, it's full of mosquitoes, and it's wet, and a lot of other bad stuff out there. Our second assumption is that there is a market for land. We define the function of this land is the land's capacity for growing biomass or crops. We also say that this market for land is global. So if I demand some land here where I am right now in Denmark, it actually may have global effects, as Michele already showed in the definition of indirect land use changes. So land is not something that can really be sticked to where you are actually occupying it, because you are affecting a market. And why is it a market? And why is this market global? First of all, crops can be grown in different regions. So the same crop can be grown in different regions. So we can have rapeseed in Denmark, we can have rapeseed in France, so forth, and Canada. Secondly, food and biomass is substitutable and is also traded on the global market. So palm oil is, for instance, substitutable with rapeseed oil. So by then we can easily go from occupying land in Denmark to clearing some forest in Malaysia, Indonesia, by substituting food. The fourth assumption we're operating with is that we can also observe different market segments for land. Some land can be used for arable cropping only. That's typical arable land as we see it. Then we have some land that can only, well, it cannot only be used for arable cropping. Of course, you can also build a city on top of it, build a road, or you can plant a forest or whatever you do. But the highest use is arable land cropping. The second type is forest. Some land is really not fit for arable cropping. If you go to northern Norway, Sweden, especially a large part of Sweden is so rocky, so hilly, that it's not really possible for cultivating any crops. But still you can grow forest. That is what we call forest land. And then last but not least, we have rangeland. That is land which is often, because it's too dry for really growing or supporting forest or crops, it could be savanna type land, which is basically used for grazing. It can also be, if you go above the tree zone in mountains, so the higher Alps, that will be some land you can only use that for grassing. So that's the third type. Fifth and not last is that if you have a change in demand for land, then this can have different implications. And actually we have identified 3 different implications. First, if I need some more land, I can get it from transforming some land, which is currently not used for anything, into productive land. Secondly, I can intensify some land which is already in use, for instance by applying more fertilizer. And last, we can deal with what we are calling crop displacement or reduced consumption. So it could be, if you remember the tortilla crisis in Mexico, when the US, they were having the bioethanol boom. We saw that there were price increases in corn in the US market, which led to reduced consumption of corn in Mexico. So that's the third possible effect we can have. Sometimes you hear that land use changes is something that is not taking place. So sometimes it is questions whether it is taking place. So in order to, well, my argument against this, here I typically use the slide you see here. And I call this slide for the mass balance proof of iLUC. So my starting point is that we have some land here before we ask for our functional unit. Our functional unit is 1 ton of crop. So we have a situation before, and then we have a situation after. So the situation after needs to supply us 1 ton more than before. Otherwise we cannot have the ton. We see that we get this ton of this area A here. And since this area A was supporting or producing crops before, we will not have these crops now. So these missing 1 ton of other crops we are seeing here at the bottom, they have to be compensated in another way. So they have to be compensated either by land use changes, as you see down here somewhere. It can be compensated by intensification, as Michele already mentioned and illustrated, or it can be compensated by changes in food consumption. So this is the only way to achieve a mass balance. So we can actually make a mass balance proof of land use changes to prove that it is real. Good. Now I will go a little bit further into the modeling of land use changes. And actually, when we model land use change, we approach the problem in exactly the same way as we approach any other LCA. So if we do an LCA of a car, we start defining the functional unit. The functional unit of a car, it could be transport of people. So in this case here, we ask first, what is land? Land, it's when we are talking about cultivation of crops, then land is an asset input. So if we have cultivation of crops, of course we need tractors, we need combine harvesters, different equipments. We also need land, otherwise we cannot have any crops. So land is an asset, just like we need infrastructure in our normal LCAs. Secondly, Now we know what is the product we are analyzing. Land is an input of asset. How can we then measure that? We do that with our functional unit of land. And our functional unit for land is what we call capacity for biomass production. So when you are paying for land, when a farmer is paying for his land, he's paying for the land's capacity for growing crops. You can also see the more fertile land you are buying, the more expensive it is. So that makes good sense. The functional unit is then defined as capacity for biomass production from 1 hectare of global average land for each of these markets you see to the left in this slide here. The main markets here are arable, and then I have distinguished between 2 different forest markets here. Then we have the grassland market, and then finally we have the barren land. For barren land we have another functional unit because there you have no biomass production, so you actually have no indirect effects when you are using barren land. So now we are ready to go on with our LCA of land, because now we have our functional unit and reference flow. Good. We defined our functional unit or reference flow as biomass production capacity. And since we have different production capacity in different parts of the world, we need to take into account that. The map you see here is a map of potential net primary production. And we use that as a proxy for potential yields of crop yields in different regions. So let's say I will now know something about indirect land use changes for using land here in the region where I am right now. I am in the northern part of Denmark, a city called Aalborg. That's where we have our head office. So what I need to know now, what is the potential net primary production in the area where I am compared to the global average for the arable market segment. To calculate that, we are using this formula in the gray box here. So we say the potential net primary production in the Aalborg area divided by the global one. We have these figures, you can see them just above the gray box, so we can actually calculate the factor for Denmark. So if I'm using 1 hectare of land in 1 year in Denmark, it corresponds to 1.08 global hectares. It means that the potential yields in Denmark, they are slightly higher than the global average for arable land. Michele, he will show some more data on these factors here. Actually, we have the map you see. We have made an overlay analysis in GIS with satellite remote sensing, where we have identified land use classes for all countries in the world, and we have overlaid with national borders. So in every country, we can see what is the potential net primary production. We can see what are the land uses, and we can see the national borders. So for arable land in every country, we can calculate what is the average potential net primary production, and we can relate that to the global average. So that is the background of these factors you see here. Good. Now we are even more ready for proceeding with our modeling of indirect land use changes. So in the example you see here, here I'm doing an LCA of wheat. In this case, we have put together a pretty normal life cycle inventory of wheat. We have collected data for 1 hectare in 1 year for Denmark. You see in the top of the process here, we have the yield, so a little bit above 7 tons of wheat per hectare. That's the common yield in Denmark. Then you see all the normal inputs. And these normal inputs are diesel for traction. We have inputs of nitrogen fertilizer, phosphorus fertilizer, potassium fertilizer, and we have some normal crop emissions. But then we also see that we have an input of land. We have the input of land here. Okay, something is happening here. I need to be sure that I can. Okay, sorry about that. Okay, the drawing tool was teasing a bit. What you see is that we have an input of land to wheat cultivation. The input of land for the 1 hectare in Denmark, you see we put the 1.8 hectare year equivalent, which you saw on the former slide. This land, we draw that from the global market for land, which is the box you see in the middle of the screen here. So we have the global market for land here, and we see inputs to the global market for land. You see that we have inputs of transformation, intensification, and the changes in consumption, which I was also referring to before. Now you see, if we go to the left in the bottom, you see that we have set the changes in consumption to 0. So actually we claim that the long-term effects of demanding land will not affect prices as it did for the tortilla crisis in Mexico years ago. And you can actually observe that the tortilla crisis is also over now. So you only see these changes in prices when there's an abrupt imbalance between demand and supply. So when there's undersupply, prices will go up. But then more suppliers will come in and will cut more forest, and prices of land will go down again. So in general, there's a balance. And that's, in addition to that, that's the default assumption for everything in LCA. Typically, if you demand 1 kilogram of fertilizer, you also assume that 1 kilogram of fertilizer is produced. That's the common. So we also do that for land use changes. So when we demand 1 unit of land, we also assume that 1 unit of land is produced. Then, looking at the left here in the screen, the 2 inputs of land which are included are, in the top we have transformation. That's where we're transforming some natural land into productive land, and that will give us emissions because we have changes in carbon stocks, so forth. The second one is the intensification. There you see that we have inputs of diesel for more transportation, things like that, and more inputs at fertilizers and more emissions. So that's the intensification part we have here. So what you see here is actually, it looks very much like a very, very normal LCA. We just include some processes or activities which are commonly excluded from an LCA. So we have one market for land here, the arable market for land, and then we have transformation and intensification as inputs. So basically that's the way the model works. There's still one issue we need to overcome. Recalling what Michele just told us before about this amortization, which is the current practice for land use emissions in LCA, is that is not really reflecting causes and effects. You cannot ask for land today and then use 20 years amortization and say that the more land I'm asking for today, the more deforestation you will see 20 years ago. It's not possible. So we would like to overcome this kind of logics. So away with that one. So what we do instead is that now I would like to know what are the land transformation effects when I ask for 1 hectare year. And I will not use any form of amortization as referred to in the figure you see here. So in order to do so, we need to look at this chart you see here. It's an illustration of what is it going like with our forests. You see there's a general trend that we are losing our forests, meaning that we are expanding our cultivated area. So we see a general decline. So that's the background, or you could say reference scenario here. So what happens if I'm asking for 1 hectare in 1 year? The first thing that happens, well, let's say I'm asking right now, and now is T1. That means that we can only have this additional hectare I'm asking for if we cut down 1 more hectare of the jungle. Right now I'm disregarding intensification and all this stuff. So I cannot have my hectare without clearing 1 more hectare of land. So there we see a real transformation of land. But then when I'm done using my land, you see in the top of the slide, I'm only asking for 1 hectare in 1 year. So this here also comes to an end. So when I stop asking my land, then I can give this land to the next crop. And then the next crop does not need to clear some land. So actually what we see here is that we have deforestation at T1, and then we have avoided deforestation at T2. So we are only having the land, we need the land transformation only for a limited period of time. So how can we then deal with this here? Actually, it means that the net effect is that in year T1, we are having CO2 emissions because there you see more deforestation, but in year 2, you will see less deforestation. Of course, in reality, you will not see that trees are growing up instantaneously after you have grown your crop, because there will be some other crops which are taking over. But if you're looking isolated at the effect of the 1 hectare you are asking for, then you will see this net effect here. And that is actually the same as moving CO2 emissions from deforestation from year 2 to 1. And that's why we are calling it, if you look in the heading of this slide here, it's called accelerated deforestation. So in our model, we actually say that you are not contributing to more deforestation, but you are contributing to accelerating the deforestation. We say that the same deforestation will take place in the long term, regardless what we do. Okay. But how do we then model that? Because our net CO2 emissions are 0. Okay, I guess you are all familiar with the global warming potential. It's calculated by 2 integrals divided by each other. Originally, it's used to differentiate different greenhouse gas emissions. So typically in this fraction here, you see that you have methane in the top and then CO2 in the bottom, and then you can, within a given time horizon, you can calculate that methane contributes 28 more times to radiative forcing and global warming than CO2. So then you can calculate your global warming potential for methane. But what I would like to do right now is that I would calculate global warming potential not for methane, but for CO2 emitted at different times. You see that on this slide here. So what you see in the top, in the denominator of the fraction here, is that we are having CO2 emitted at time delta t, and we still use the same reference below in the denominator, CO2 emitted at time 0. And you may recall from your math class that an integral can be represented as the area below a chart, and that's what you see in the bottom. So you can actually divide these 2 areas with each other, and then you can have the global warming potential from CO2 emitted after delta t years relative to CO2 emitted at year 0. So we can actually stay within the normal, well-known, well-acknowledged global warming potential, and then we can calculate it. I've just shown it for global warming potential for, if you emit it at time 0, then it's 1. If you wait 1 year, then you have a slightly lower global warming potential. And that actually means that if you look in the bottom here, that if I'm accelerating 1 kilogram of CO2, if I emit that today instead of next year, it will give us an impact of 0.007 something kilogram of CO2 equivalents. So that's the effect of time. Someone is calling, it's not me. What I show here in the next slide is that we are not necessarily bound to the global warming potential. We can also deal with other climate change metrics. So we have another version of the model where we are using global temperature potential after a 20-year time horizon. And then you can see that will give a factor 3.5 difference. So our modeling is also highly dependent on climate metrics. I will not go further into that. That would require some more time for explaining. So with these slides I've been presenting right now, you should have a relatively clear picture of what are the basic modules and parts of our indirect land use change model. So now Michele, he will give some a brief, you could say, guideline on how to use the model and some application examples.
Thanks, Jannick, for this very comprehensive introduction to the technical aspect of the model. I think this is necessary, of course, for you to understand what we do in this model. But now I think it's also interesting to show you how do we actually use this model in practice. And you will see that it's a little bit easier than it seems from the technical explanation. So first of all, let's say, what does the model provide? Why should you use this model? Well, first of all, the model can provide a very simple result, which is elementary flows per unit of land use, expressed as a productivity weighted hectare per year equivalent, as you have seen. But in a more advanced result can also be obtained. For example, we can obtain the indirect land use change effects of land using activities that are linked to the foreground activities of the model in LCA softwares. So in order to obtain that, you need some input data, not many actually. What you need is, first of all, the land occupation. Second, to define the market of this land. And third, the productivity factor. These are all concepts that have already been introduced by Jannick before. Let's see in practice, how do we do that? Well, concerning the land occupation, you basically need to answer the question, how much land is used per functional unit in your case? For example, 1 hectare. Then you need to identify what kind of land. So you need to identify the market segment to which this land belongs. For example, arable, forest, or rangeland. And Jannick already explained before what is the difference of definition in these 3 land types. Third, you need to identify a productivity factor of the land that you are using. Now, the productivity factor can be simply read in a table. Jannick showed the map from Aber et al. Before. So the productivity factor is basically, if we assume that the productivity factor of the global land is 1, you can see that the productivity factor for, say, Denmark is 1.08, as Jannick already showed before. So it's slightly higher than the global average. This is mainly due to the high intensification level achieved in Denmark. While if you look at Indonesia, the productivity factor is 1.97. So it's almost double than the global average, which means that occupying 1 hectare in Indonesia gives you almost twice the productivity than occupied in Denmark, and almost twice of the global average. So that's where you need the productivity factor. Then with the productivity factor, you can do some basic calculation. First, you can calculate the weighted productivity of land, so the productivity weighted hectare per year, by multiplying the factor times the net primary productivity of your land. Second, you can multiply the productivity weighted with the global indirect land use change lifecycle inventory that you have obtained per the productivity weighted hectare per year. So only 3 input data basically, and 2 simple calculations, 2 multiplications. So in SimaPro or in any LCA softwares, what you actually need to do is the following. Let's say for the example of wheat. You might recall this picture that Jannick showed before, where you can see the input from the technosphere that you need to insert in your LCA if you are calculating the impact for wheat production in an occupation of land in 1 year or 1 hectare for wheat production. Now, if you put this input from technosphere in your LCA software, what you basically need to do is the following. You just, the number that you saw before, they are here in SimaPro. So you have diesel, nitrogen fertilizer, phosphate fertilizer, potassium fertilizer. You have some emission to air in the bottom. And of course, you have an input of arable land from the technosphere. And the amount of arable land that you need from the technosphere is 1.08, because we are assuming that our production of wheat is occurring in Denmark. And you remember that from the example we showed before, that the productivity in Denmark is 1.08, the productivity weighted of land in Denmark. So what you would obtain at the end is, of course, a graph, a network, where you can see that in the bottom left, there are the results of our indirect land use change model. You can see that it is the contribution of intensification of arable land and transformation from secondary forest to cropland. So you can see here there is both an indirect land use change in terms of intensification and in terms of transformation of land at the frontier, as we showed at the beginning. So basically, you need to do very few calculations, only 3 inputs, and then just use an LCA software. That's it. So at the end, everything that has been explained so far, it might look complex, but using this model, it's actually pretty easy. The model has already, of course, been used in the last 10 years in many applications. We have applied it to most industrial sectors, not only food, but also building sector, apparel sector, the chemical sector, and so on. If you want to have more information of the application of the model, you can go on the address at the bottom of this slide, and you will find specific application for each field presented in this slide. So in terms of some more concrete case study, for example, we applied the land use change model to palm oil production, palm oil produced by United Plantation in Indonesia and Malaysia. It was the result of this is the result of a detailed LCA studies from 2004 until 2014. What you can see in the slide is the contribution of land use changes, both indirect land use change in green and other impacts, including CO2, ammonia, nitrate, and nitrogen. And you can see that here most of the impact is direct, and only a limited amount is the contribution of the indirect land use change due to the high yield obtained in palm oil production by United Plantation in Indonesia and Malaysia. And of course, reduce the indirect land use change effect. Another application is the calculation of land use change effect of animal feeds in the Danish market. Animal feeds can be, of course, different crops. Here, first you see barley in Denmark or barley in the EU average production in EU 28 and in Russia. The results are expressed, as you can see, in a kilogram of CO2 equivalent. And again, in blue, you see CO2 emission, ammonia, nitrogen, and nitrates. And in red, you see the indirect land use change contribution. You can also see that indirect land use change contribution increase in Russia, for example, and this is because compared to the Danish or EU 28 average production in Russia, we have a lower yield, and therefore occupying land in Russia results in lower yield. Therefore, to obtain the same amount, we need to occupy more land, and therefore the indirect effect will increase, as also the direct, of course, as you can see. The same result can be obtained for wheat in Germany or in the UK, for example. Here, you can see that there is a lower difference between the two in this case. A very much lower result, instead, you can see for the rotation grass in Denmark and maize and silage production in Denmark. This is because, mostly because these two crops have a high water content, so the mass is relatively high per hectare. So you have, since the results are expressed in kilogram of crop per kilogram of crop, then you see a lower result due in terms of land use change due to the high weight of the crop, so the high water due to the high water consumption. And on the other end, you can see instead the results of rapeseed, sunflower, and oil palm. In this case, the first one for EU 28, the sunflower production in France, and oil palm fresh fruit bunches in Malaysia and Indonesia. You can see that the last one has a lower indirect land use change effect. Again, because as I showed in the slide before, the yield of oil palm compared to sunflower and rapeseed is higher. especially in Malaysia and Indonesia. So per unit of products, the land use change effect is lower. With that, I give the word to Jannick again to show you what are actually the most recent developments that we have carried out in this model.
Thank you, Michele. So now we have a good hold on how the model works, how to apply it in practice, and what does it imply for our normal LCA results. Of course, until now we have only presented the results in terms of greenhouse gas emissions, and that is because that is where most discussions are. We are also using the model for quantifying biodiversity impacts. I will come back to that in a few seconds. That's also something we are working on. First, I will now go into some of the new developments we have been doing. Until recently, the land use change model was not as such really linked to global land use and global crop production. But recently, we have made an extremely detailed study. You can see what I've done here is that I've represented the globe divided into squares. For that, we have used the multi-regional hybrid input-output model called SimaPro. It's a big LCA model which includes all product categories in economy, and it includes 47, well, the global economy is divided into 47 different countries and regions, where each country or region is then divided into 164 industries. So there we have actually, for each country, we have thoroughly identified how much land is provided by each country. So that is, you see that the left globe here says supply of land. So every country will supply some land. For instance, when we did that for Denmark, we could identify that Denmark has not supplied any additional land in terms of transformation. So agricultural land in Denmark has not expanded. But what expanded in Denmark was more crops from intensification. So every year we are having higher, on average, we're having higher yields in Denmark. And of course, that's also the case for many other countries. Then for other countries, we see less pronounced changes in terms of yield. If you go to developing countries, you will see that there you have much higher changes in supply of land in terms of transformation of nature. We did that based on time series for all crops in all countries in the world. Basically, we extracted these data. We made a mass bulk download from Faustat, where you have all crops in the world for all countries. For that, we kept track on area, yield, and production. So there you can actually see when we converted all crops into dry matter, because supplying a lot of water in potatoes, for instance, does not really give any more food. It's just water content. And then we have dry matter. We can also compare different crops. When we have the production and we have the yield and area, we can actually trace historically how much of additional crops comes from intensification, that's increase in yields, and how much comes from changes in the cultivated area. And we can do that for all countries in the world and the sum of all crops. So that is the supply side of land. And then we put all this land, we defined a global market for arable land. We also did it for forest land and rangeland, but here I'm mainly talking about the arable land. So it all goes into a global market for land. And then we can move to the right side of this slide here, where it says use of land. And use of land, that is where every crop in every country is using some land. You see we have wheat cultivation here in the top, in Denmark maybe, and then oil palm in Indonesia, Malaysia in the bottom. So that was the way we were linking that, and then we saw we could actually include land use changes for every crop in every country, or basically for every product in every country in the world. And here in this slide I show what is the contribution of indirect land use changes, in this case here for raw milk production, that is milk at farm gate in the different countries we have in SimaPro. You see the different colors. We have blue methane, red nitrous oxide, yellow CO2, and the green one is indirect land use changes. And we can see that that is varying from country to country, as expected. You can also see the magnitude of how indirect land use change is contributing to the overall carbon footprint here. The next slide shows the same, but here for different cereals. And you see that for cereals, indirect land use changes is more or less doubling, or even more than doubling, the greenhouse gas emissions per kilogram of crop. So we can actually, now we have implemented in a global model, including all products in all countries in the world. So that is where the status is currently, at what level we can implement the indirect land use change model. Michele, he will take the last word to say a few words on what are we currently working on, what is in the short-term pipeline, and what are we then planning for the, let's say after 1 year. So Michele, please go ahead with that.
Thanks, Jannick. So let's see, what is next? So at the moment, we are working on cross-checking with satellite remote sensing data, our land use change from land use type to land use type. I have developed the land use change matrix for each country in the world from 2001 to 2012 for 17 land use types. And this is currently being used for further validating and cross-checking the land use change type. And as it's written here on this bullet, this matrix was developed triangulating a number of data, among which also satellite remote sensing data. Then we are working to include emission from particulates from forest fires, which are very important, as Jannick mentioned in one of the first slides, cause of a lot of deaths and losses. They are currently not included in the model. We are working to include them. Third, we are trying to improve the data on carbon stock and biodiversity, and to include a module for the nature conservation, for modeling also the nature conservation. Of course, this is what we are currently doing right now, but many more things could be done. We are thinking of future potential developments as well. For example, we would like to have an annual automatic update of the background data. We, of course, do update of data already now, but we would like to have an automatic annual update in the background. We would also like to have a more complete modeling of the intensification part, so the contribution to indirect land use change coming from intensification. At the moment, we include, of course, fertilizer in the impact from intensification, but of course there are other inputs for intensifying the production. For example, water, so the effect of irrigation, the input of pesticides, and so on. And third, we would like to further subdivide regionally the different market for lands, because of course the more precise is the market model, the better we can identify the final effect of indirect land use change. And with that, we have concluded. I don't know if Jannick has any final word. From my side, I would like to thank you for your attention. And Jannick, if you want to share any final remark, otherwise we can say goodbye.
Thank you, Michele. Of course, I would like to say thank you for your attention. We have a little bit of time, which will allow for a few questions. I can see that there's already one question asking whether you will get the slides after the webinar. Yes, we will send the slides to all who are subscribed for the webinar, so you will have the slides. We have also recorded the webinar, which we will also share with you. So if you have any questions, you can either type your question in the chat in here, or you can unmute yourself and ask and take the word. Okay, now we already got the first question. The question is, where could one find the table with production factors? What we do for, you would say, for free is that there's in the slides you can already see what are the references to where we have obtained the maps. So you can calculate them yourself. Otherwise, if you want to have access to our pre-calculated factors, that is part of the model. And that can be accessed if you subscribe to the our initiative, which you can find more information on the webpage. You can see on this slide here. Okay, there's one more question. The question says, how do you allocate between direct and indirect land use changes? If both are included, isn't that double counting? Okay, this is a super good question. I would say actually it is not double counting. I would actually like to go back to one of the slides in the beginning, the slide Michele showed in the beginning. So you see the slide popping up here, that we have where the rapeseed goes in and the other crops goes out. That is what we call direct land use changes. And then everything else to compensate for these crops that we are displacing out here, that is what we are calling indirect land use changes. So the direct land use changes will typically be changing from one crop to another. It gives a minor change in biodiversity. There are some certain flies, they better like rapeseed than barley, for instance, and we have slightly change in carbon stock, but it's very, very small. So the major impact will be in the indirect land use changes. But all changes together summed up will give you the correct total impact, and which is not double counting. I hope that kind of answered the question. Okay, we have another question saying, I missed a big chunk of the webinar. Is the video available for watching later? Yes, we have recorded the webinar and we attempt to share the video with all of you. Yes. Good. With that, I can see that time is more or less out now. So I would like to say thank you for your attention and have a nice day. Thank you.
Bye-bye.
Bye-bye.